So we completed our simulation, right? The next step that we have is an RTL analysis, right? Now here, the most important option that we frequently utilize is the schematic, right? So you'll be finding with an RTL analysis, we have a schematic, and then after we perform a synthesis, we also have a schematic, and after implementation also we have schematic, right? So two of the schematics which are very, very useful is the schematic that you get with an RTL analysis and the schematic that you get with a synthesis, right? So with an RTL analysis, you get the schematic that you understand, right? And when we consider a synthesis, now here your HTL code is transformed into an FPGA primitives, right? Finally, we have an FPGA architecture, so we need to convert our HTL code into something that our FPGA understand, right? So we have a set of primitives available for each FPGA device. So synthesis transform our HTL code into the set of a primitives, okay, consisting of a cells and a net, okay, and that could be understood by an FPGA, right? So synthesis view represent your transformation of your HTL code into the FPGA base primitives, right? Whereas schematic represent the basic symbols that we used in a digital electronic to represent your code, right? For example, here you have a simple AND gate. We already know the symbol for an AND gate, right? So this will be converting an entire system to a simple AND gate, right? So if you just go to an RTL analysis and if you analyze the schematic, so here you'll be finding the symbols that you already used in a digital electronics. Okay, so here you could see this is the familiar symbol for our AND gate, okay, and then you have this two input A and B, and then we have a Y, right? So RTL analysis basically give you the first view of the HTL code. So you could just go through and analyze whether you are getting the schematic as expected, right? The next step is the synthesis, right? Now synthesis transform your HTL code to something that our FPGA understand, right? So we just need to perform a synthesis and we'll be choosing the default option over here, right? So now our synthesis is completed, right? So we'll just be opening our synthesized design. So you have an option to open the synthesized design from here, or we could just go ahead and click on this open synthesis design, right? This will automatically open a synthesis design, right? Now here you could see the default view that we get is the package view, right? So this all represent the pin that our FPGA have, right? So you could just hover on any one of them and then you could find out that this is pin number E12 and the site, and it also specify the pack. Okay, do not worry much about this. The second view that you get is the device, right? So here you could see our logic. Okay, so this is an FPGA tile that we have, right? So we haven't yet specified the constraint, okay, and then after that only we will able to see where our logic has been added into an entire FPGA tile, right? So these are the two default view. Something which is very important in this one, right? So you by default get an IO port view where you go to a scalar port. You could clearly see all the port that you have in your design. So AB represent an input and Y represent an output, right? If you do not able to find this view, you could just go to a layout and select an IO planning, right? So this will automatically bring package device and IO port, right? Now here you have a package pin, right? So package pin represent the peripheral pin that you have on an FPGA where you want to connect this input, right? So since this two represents an input, we'll be connecting this to a switch and Y to the LED, right? So you could just go ahead and look for the board specific master XDecified, right? So here I am utilizing the Zybo Z710. So I'll just search for a master XDecified, okay, and most probably will be finding the XDC file is available on GitHub, right? You could just go in and then you have a switches. So for switches you have this unique number, right? So for switch 0 you have G15 and P15, right? So this represent the package pin. So we'll just go ahead and here we will specify G15 and P15. So some of the peripheral names are also mentioned on a board. So this is the development board that you are utilizing. Okay, so here you could see we have our 4 switches, right, and the 4 LEDs over here. So just below the switch, okay, you could find out that this is our switch number 3 and the unique package pin to which it is connected, right? So T16, W13, P15 and G50, right? So this represents the second way of finding the pin number, right? So not all the peripheral will have this pin number been mentioned, but wherever they are mentioned, you could always utilize them, right? The good way is you go ahead and look for a master XZC file. There you'll be finding all the peripheral related information. But for a simple peripheral like switch, LEDs, the push buttons, okay, you could always look for the unique number written just next to the peripheral name, right? So here you could see we have an LD3 which is connected to D18, right? So this LED is connected to pin number D18. So that is what we will be specifying over here. And see that the default level which is chosen for an IO standard, you just change it, right? So I'll be changing it to the max intensity, that is LVC MOS 33. So this basically represents that we are considering applying 3.3 volt, right? So this completes our process of adding a constraint, right? So in our source code we have A, B and Y, and we are able to connect it to the FPGA pins, that is G15, P15 and D18, right? So this is what is mean by a constraint file. So to create a constraint file, after you specify this in a scalar port, you just need to save your code, press Ctrl and S and give a name to a file. So we'll just be naming this as stop. Okay, now if you go to a source tab, so with a constraint, okay, folder, now you have a top.xdc. So if you just open, you could find out that all the ports are connected to the respective pins, right? So this complete our synthesis. Okay, so synthesis basically transform your HTML code to the FPGA primitives, right? And that could be understood from an netlist also, right? So you have a series of nets and then you have a cells, right? So cell include the input and output buffer and the AND gate, right? So which is implemented with the help of an LUT, right? So LUT is basically as an internal resource, right? The next important thing to analyze is the schematic. So let us just go ahead and try to find out the schematic. So now if you analyze this schematic, which is available in a synthesis, you could clearly see this is different than what we see in an RTL analysis, right? So this is how your code will be transformed into something that your FPGA understand, right? So LUT are the fundamental block that you have in an FPGA and which are utilized to implement the logical expression, right? And then you have a series of buffer, right? So this complete the synthesis, the process of synthesis. And now remember, before performing an implementation, we must specify the constraint file so that this help our Vivado to choose the specific side on our FPGA where our logic will be placed, right?